Okay, and so a nice YouTube video that explains all that quite nicely in simpler examples is this video, Singular Value Decomposition by Luis Serrano. So if you just Google Luis Serrano and SVD, this should be the first result that pops up. Okay, let's return to our code here. And so we're explaining what is this line of code doing here doing. It's basically the spectral decomposition. We're taking the first few columns, the first few singular values, and then the first few rows of V and multiplying that together, and we get an array. And what we need to do is these are the array numbers corresponding to the red components of each pixel. And we need to convert them, these right now, these are decimals or floats. We need to round them down, convert them to integers. That's what this line here does. It takes the compressed red matrix and this method as type int just turns everything into an int. So if you ask what is compressed red now, well, the 202.41 has changed to 202. Okay, so now here's the user-defined command or function, I should say, that takes in the rank or number R of how many columns, singular values, and rows I want, and compresses the file accordingly. So here, for example, just to illustrate, this is a rank 5 when I add in or enter in compress 5. It just takes the first 5 singular values and I get this pretty blurry image. If I increase that 5 to a 20, I get a little bit better. Now at least you can tell it's a dog. And then when I compress at rank 100, I get this a little bit better. And something even larger would be something like 394. And we have a much clearer picture in that. So that's what this compress function that we're going to next explain does. It tells you how many singular values do you want to use from your singular value decomposition. And based on that, cooks up the corresponding image. Okay, so the notation for defining a function is def, then the name of the function, and the stuff you're going to take as input. Here, we're just going to take in a number that I'm labeling as rank. Then you want to follow it by a colon, and then hit return, and then importantly, you need an indentation here. That tells Python that what follows or what's indented is part of the definition of compress function. Okay, so then we have this compressed red that I've just explained how I get that. That's just taking the output of the singular value decomposition, multiplying them, and we do the exact same thing for the blue and for the green. And again, I've apologized, but I've interchanged the naming of the blue and the green, but as long as I'm consistent, we'll get the appropriate answer out. Okay, so then I have these 3 compressed matrices consisting of the red, blue, and green components, and then I want to put them back together into a 3-dimensional array, and the command for that is the stack command. Oftentimes in Python, you have arrays of 1 dimensions or 2 dimensions, and you want to put them together in certain ways. You want to stack them together in an appropriate way to build a 3-dimensional array, again, a list of lists of lists, essentially. And the appropriate way is to this time glue or stack them along this axis equals 2. You can have the parameter of axis equals 0, 1, or 2 when you have a 3-dimensional array. And in this case, what we want to do is the axis equals 2. What are we doing? We're taking these 2-dimensional arrays, compressed red, compressed blue, and compressed green, and at each pixel, we want that pixel, the data in that pixel or associated with that pixel, to be the RGB triple of numbers associated to the color of that pixel. And so, yeah, this line does that. So we get a compressed, what I'm calling compressed underscore array. And then what we're going to do, let me just skip a few lines. At the end here, we're going to plot this matrix here secretly represents an image, one of these blurry images. And this im.show command takes this three-dimensional array and turns it into a picture. So that's this built-in command that we're using. Okay, then jumping back up to these columns here, these rows, these lines that begin with rows, comma, columns, equals the shape of one of these matrices. That's just the shape of our image. So that was in this particular example, 1399 by 1920. And now I want to calculate how much we're compressing, how less information we need to store the data in each image. So the way to do that is if you're having a rank 5, if you're using a rank equals 5, you need 5, how many numbers do you need? Well, you're going to have 5 rows, and the number of numbers in that 5 rows is 5 times the number of numbers in this row variable, which was in this particular example, 1399. And then we're also going to need 5 columns. So, oops, where is this? 5 columns. So that's why we're doing the rank times the number that's stored in the columns variable, which is in this particular example, 1920. And then we need rank number of singular values. So this rank times 1 is where that's coming from. This again is explained nicely in Luis Serrano's video. Okay, so that's how much information the compressed data uses. And then we're dividing by the total amount of data in the original image. So that was the total number of rows times the total number of columns. Now, technically, each pixel had 3 numbers associated with it. So there should be a times 3 here, but there's also going to be a times 3 in the numerator, and I've just sort of canceled them out already. Okay, and so that will multiply by 100 will give us the compression ratio. And then this next line just says print this compression ratio. You can see that when the we call compress with rank 5, that ratio is 0.618%. And so that's why, we've lost a whole bunch of information, and that's why it's very blurry. Then when we call compress with using 20 singular values, it's a little bit better. The compression percent is 2.4%. So that's quite a bit of compression or loss of information. At least you can tell it's a dog. Okay, and then finally 100 is something like this at 12% compression. And then this final line here allows you to create a slider where you can vary the rank. So it's kind of an interactive gadget. So it's using the functionality of this method or program called interact. That's part of this package, IPy widgets. Anyway, so you call this compress function or whatever your function is called. And the variable ranges from, I just chose 1 to 500. And you just pick a point on the slider. So here I've chosen 394. And that corresponds to 48% compression. And so the image there looks like this. Let's choose something else, like even more, like 4082. And it'll well, I had to restart everything, but okay. So at 432, it's 53% compression, and the picture is like so. Okay.